Hello and welcome to The Explainer. Today, we're pulling back the curtain on the world of engineering to reveal the two fundamental pillars that make, well, everything possible. Let's just dive right in.
Think about it. From these massive structures that seem to defy gravity to tiny electronics that feel like pure magic, how does it all happen? Well, it's not magic. It's a mastery of principles that every engineer has to live and breathe.
The secret is that it all boils down to two core concepts. These are the two secret weapons in every single engineer's toolkit. If you can get these right, you can build almost anything. So what are they?
Okay, first up, we have the universal language of engineering, measurement. You see, before you can build anything, you have to be able to describe it perfectly with numbers. Its size, its shape, its location, precision is absolutely everything.
Now, you'd think engineers would have one single language, but they actually use two. While the SI system is the global standard, the US still widely uses its own. The real secret here isn't about which system you use. It's about being incredibly consistent and always choosing the right unit for the job.
To really appreciate the power of this language, let's just talk about scale for a second, because this is where it gets wild. Engineers work with some mind-bogglingly large numbers. We're talking gigameters. That's 1 billion meters. It's a unit you'd actually need to talk about the distance from here to the moon.
But here's the cool part. That same system scales down perfectly to a human level. A kilometer, 1,000 meters, is a distance we can all wrap our heads around, right? Like a few laps around a running track. It's the same language, just a different prefix.
And now let's go to the other extreme. A micrometer. That's 1/1,000,000th of a meter. It's so small you need it to measure a tiny speck of dust next to a human hair. This is the insane precision you need for things like microchips. That's the power of this language. One single system takes us all the way from planets to particles.
So why does all this precision matter so much? Here's a perfect everyday example. A tiny 1% error on your bathroom scale could throw your weight off by a whole kilogram. Okay, maybe not the end of the world for you. But now imagine a 1% error in a bridge support or an airplane part. The consequences could be, well, catastrophic.
So how on earth do they manage all this complexity? Well, they rely on incredibly powerful software, like computer-aided design, or CAD. This stuff lets them create and test these super detailed 3D digital blueprints, making sure every single number is perfect before anyone even thinks about building something.
Okay, so you've measured everything perfectly. You have the numbers down. Now for the second secret weapon. You have to understand a material's personality. This is all about knowing what something is made of and, more importantly, what it's capable of actually doing.
Right? You've got the perfect blueprint, but what do you build it with? Wood? Steel? Some kind of plastic? Choosing the right stuff is a huge decision that depends entirely on its unique properties.
Let's start with the mechanical properties, basically how a material reacts when you push it, pull it, or bend it. Tensile strength is how well it resists being pulled apart. Hardness is pretty straightforward. It's about resisting scratches. Toughness lets it absorb impact, and ductility is how much it can stretch before it finally snaps.
Now, toughness and ductility might sound kind of similar, but they're totally different. A car bumper needs to be tough. It has to absorb the energy of a crash without just shattering into 1,000,000 pieces. Ductility, on the other hand, is more like stretching a piece of taffy. It deforms and stretches a whole lot before it finally breaks. Both are crucial, but for very different reasons.
And it's not just about force, right? Engineers have to think about the environment. Is it going to get hot? Well, then you need good thermal conductivity, like in a computer's heatsink. Will it be exposed to chemicals? It better have good corrosion resistance. And if it's going inside a human body, like a medical implant, it absolutely has to be biocompatible. That one's non-negotiable. So, with all these properties in mind, where do engineers even find the right materials? Well, they generally pull from 4 main families. You can think of it like casting for a movie. You need to assemble the perfect team for the job.
First up, you've got the workhorses, metals. We're talking iron, aluminum, copper. Their signature move is strength and conductivity, which is exactly why they form the backbone of everything from skyscrapers to the wiring inside your phone.
Next, the versatile polymers. This is a huge family that includes everything from a plastic water bottle to a nylon jacket.
Because they're so lightweight, flexible, and easy to mold, they're literally everywhere, especially in consumer goods.
Then come the tough guys, ceramics. These materials are all about handling the extremes. They're incredibly hard, and they stand up to intense heat and electricity like champs. That's why you'll find them in things like super sharp cutting tools and even the heat shields on spacecraft.
And finally, we've got the custom-built superstars, composites. These are engineered materials like carbon fiber or fiberglass that literally combine two or more materials to get the best of both worlds, creating something stronger, lighter, or more durable than any single material could ever be on its own. To see how these families all come together, just look at the Maca clock tower. It's a perfect example. It uses limestone for that beautiful facade and modern glass, which is a type of ceramic, for its windows. This is a true masterpiece where the choice of materials creates both stunning beauty and incredible function. So you see, every single engineering project is this careful balancing act. It always starts with precise measurement. Then you have to consider the material's properties, the mechanical forces, the environment, and of course, the practical stuff, like cost and whether you can even get your hands on it. And that really brings us to the big takeaway here. Just look around you for a second. Your phone, the chair you're sitting on, the building you're in, every single object tells a story. It's a story written in the language of precise numbers, and it's brought to life by the personality of a carefully chosen material. It makes you wonder, doesn't it? As we get better and better at measuring things, down to the atomic scale, and as we invent entirely new materials with properties we've never even seen before, what incredible feats of engineering are just around the corner? What will we build next?